I want you to just take a second and imagine the actual physical reality of the internet.
Oh, wow. Yeah, that's a big concept.
Right. And more specifically, the physical reality of artificial intelligence. Because right now, when you ask an AI to, write a block of code for you
Mm.
or have it generate one of those hyper-realistic images, the experience feels like magic.
It really does. It feels completely weightless.
Exactly. But behind that instant answer on your screen, there are massive buildings, like just sprawling data centers across acres of land, generating literal tons of heat.
Tons of it.
And they are drawing just mind-boggling amounts of electricity. And they're all fighting this desperate battle against the fundamental limit of physics.
Which is, well, the copper wire bottleneck, right?
Exactly. How fast electrical signals can travel over simple copper wires.
That is the great hidden irony of modern computing, I think. We throw around this term, the cloud, which sounds so...
Ethereal.
Yeah, so ethereal and floaty, but it is entirely tethered to very heavy, very hot physical infrastructure on the ground.
Right.
And we are currently hitting a brick wall with that infrastructure. The processors inside those buildings are now crunching data much faster than the copper wires connecting them can actually handle.
Which brings us to the mission of our deep dive today. We are exploring the cutting-edge hardware being built, like right now, to solve this massive AI bottleneck.
The physical solutions.
Yes, we're talking about a complete transition to optical solutions, specifically utilizing silicon photonics and microscopic lasers to completely replace those copper wires.
And what's wild is how this exact same technology is simultaneously powering the brains of autonomous vehicles.
It's crazy.
It is a phenomenal convergence. You have two completely different industries, generative AI and self-driving cars, that have suddenly realized they both need the exact same physical breakthrough to survive.
So to understand how this is actually happening, we're pulling from a really fascinating stack of materials today. We've got a highly technical November 2022 product release from a Glasgow-based manufacturer called Sivers Photonics.
Right, looking at their raw hardware capability.
Exactly. And we're pairing that hardware reality with a trio of very recent August 2026 financial and business releases from Aeva Technologies, which is a company known for automotive sensing that is currently executing a massive pivot directly into the heart of AI data centers.
The big picture to keep in mind for you as we go through this is that we are witnessing a fundamental shift in how humanity handles information.
Right.
We are moving from an era of moving data with electrons to an era of moving data with photons. I mean, light.
Light, which sounds like sci-fi.
It does, but moving data with light requires a level of hardware precision that is almost hard to comprehend. You can't just bend a beam of light around a corner the way you can bend a copper wire.
Right, you need specific physical tools.
Exactly. So today we are dissecting the companies that are essentially manufacturing the physical picks and shovels for this new optical gold rush.
Okay, let's unpack this by starting at the absolute ground floor, the component level. Because before you can build an optical data center, you need the raw hardware.
You need the lasers.
You need the lasers, and that's where Sivers Photonics comes in. They are a UK-based manufacturer with a 20-year history, operating this highly specialized ISO 9001 certified fab in Scotland. And they aren't just in the testing phase either. They're actively shipping over 1 million lasers every single month.
Wow.
Yeah, with over 45 million currently deployed out in the real world.
And that production volume is the crucial first piece of the puzzle here. This isn't theoretical physics happening in some, university basement.
Right.
This is industrial scale manufacturing of highly complex optical components. They've positioned themselves as a strategic supplier to Fortune 100 companies precisely because they can hit those numbers reliably.
But reading through their manufacturing details, I hit a technical wall that I really need you to break down for me.
Okay, let's hear it.
Sivers heavily advertises their, and this is a mouthful, their NP100 DFB lasers optimized for SIF integration.
Ah.
Yes. Now, SIF stands for silicon photonics.
Right.
So, if silicon photonics is the undisputed future of computing, why are they using a completely different material, indium phosphide, to make the actual lasers?
It's a great question.
Why not just make the lasers out of pure silicon and save yourself the headache of combining materials.
What's fascinating here is that it comes down to the fundamental atomic structure of the materials themselves. Silicon is an absolute miracle material for traditional electronics, right?
Right, it's in everything.
And it turns out it's also fantastic for routing light. You can etch these microscopic channels into silicon. Just think of them as tiny fiber optic cables,
Okay.
and the light will travel down them beautifully.
Right.
But silicon has a fatal flaw when it comes to optics. It has what physicists call an indirect band gap.
Okay, meaning what exactly in practical terms?
Well, without spiraling too deep into quantum mechanics,
Please don't.
it basically means the atomic lattice of silicon doesn't want to release photons. If you
No.
pump electrical energy into silicon, its atoms just prefer to vibrate.
And vibration means heat.
Exactly. Atomic vibration is just another word for heat. So if you try to build a laser out of pure silicon, you mostly just get a very tiny, very hot microscopic heater. It's terrible at generating light.
So silicon is the perfect superhighway for the light to travel on,
Right.
but it absolutely cannot act as the engine to create the light in the first place.
That is the perfect way to look at it. Indium phosphide, on the other hand, has a direct band gap.
Okay.
When you pump energy into it, it happily and efficiently spits out pure, focused photons. It is a fantastic engine.
So they need both.
Right. So the engineering challenge is this. How do you get the indium phosphide engine onto the silicon superhighway? Sivers uses a process called hybrid integration to physically attach these separate microscopic lasers onto the silicon chip.
You get the best of both worlds.
Exactly. You get the light-generating power of one material and the cheap, scalable routing of the other.
But think about the physical scale of what you just described. How do you attach a microscopic laser to a tiny silicon channel without messing up the alignment?
It's incredibly difficult.
Because if it's even slightly crooked, doesn't the light just shoot off into nowhere? It sounds like trying to thread a microscopic needle while riding a roller coaster.
It is notoriously difficult, which is exactly why a lot of companies fail at this specific step. But Sivers is tackling this through a joint development program with IMIC,
Right, Aeva.
which is one of the premier nanoelectronics research institutes in the world. They are using highly specialized laser-assisted flip-chip bonders to place these indium phosphide lasers onto the silicon wafers.
And the precision on this is wild.
Oh, yeah.
The precision they're achieving is less than 0.3 micrometer.
It's almost unbelievable.
I want to pause on that number because it's hard to visualize. A single strand of human hair is roughly 100 micrometers thick.
Right.
So they are taking two completely different materials and aligning them with a margin of error that is roughly 1/300th the width of a human hair.
And that frankly absurd level of precision translates directly into the performance metrics we were seeing in the report. Because as you pointed out, if the alignment is off, the light just scatters.
Right.
But the initial results from these bonded devices are incredible. They're operating at a 1550 nanometer wavelength. They are pushing up to 40 milliwatts of optical power directly into the silicon waveguide. And they are achieving a highly stable coupling efficiency of 1.5 decibels plus or minus half a decibel.
Okay, coupling efficiency, translate those decibels into English for me.
Yeah.
Does 1.5 decibels mean we're losing a lot of light in the transfer?
Actually, the exact opposite.
Oh, really?
Yeah. In this context, decibels measure loss, so a lower number is better. A 1.5 decibel loss means the vast majority of the light generated by the laser is successfully making it into the silicon channel.
Oh, I see.
It is a highly efficient, incredibly clean transfer of energy, and it gets even more complex when you look at how they're stacking these lasers together.
Yes. Looking at their product arrays, they demonstrate these massive setups. Specifically, they highlight a 32-channel array with 100 gigahertz spacing, built for CW WDM applications.
That is quite the alphabet soup.
Massive alphabet soup of acronyms. Break down what a 32-channel CWWDM array actually does for us.
Well, let's use a radio analogy. When you get in your car and turn on the radio, you can tune into different stations, right?
Right, 98.1, 101.5.
Exactly. And all those radio waves are flying through the air at the exact same time, but they don't interfere with each other because they are on different frequencies.
Okay, that makes sense.
CWWDM, which stands for Continuous Wavelength Division, multiplexing, does the exact same thing, but with light inside a microscopic tube.
Wait, so they are sending different colors of light down the same channel simultaneously?
Exactly. Each channel is a slightly different wavelength or color of laser light. The Sivers array can generate 32 distinct channels at the same time. And the 100 gigahertz spacing means these channels are packed incredibly close together on the optical spectrum. They are so pure and stable that they don't bleed into each other.
So you can just stack data on top of data.
Right. Each of those 32 colors can carry its own massive stream of data. They showed these operating at over 50 milliwatts per channel around the 1300 nanometer mark, all while passing the rigorous GR468 qualification standards.
And GR468 is essentially the telecom industry's gold standard for ruggedness, right? Meaning these lasers won't degrade or burn out prematurely under heavy use.
Precisely. It's the proof that this isn't just a lab trick.
So if you're listening and wondering why a microscopic Scottish laser matters to your daily life, this is the foundation. These indium phosphide lasers are the physical engines required to make instantaneous cloud computing happen.
They really are.
Because without this level of extreme manufacturing, the next leap in AI literally grinds to a halt because it just chokes on its own data.
Which naturally brings us to the next piece of the puzzle here. Sivers proves we can manufacture the raw components.
Right.
But who is taking that underlying photonics platform and actually building the infrastructure to rescue these AI data centers?
Enter Aeva Technologies, trading under the ticker AEVA. Now, if you follow the tech space, you probably know Aeva as a sensing company.
Yeah, that's what they're famous for.
Right. They built their reputation as a leader in automated driving and LiDAR systems for cars. But recently, they announced a massive strategic shift. They're launching an entirely new business unit dedicated to optical connectivity.
It's a pivot that caught a lot of people completely off guard.
I was one of them. My immediate reaction was, why is a company that specializes in giving sight to autonomous vehicles suddenly trying to sell networking hardware to AI data centers?
It sounds totally random.
On the surface, those two things have absolutely nothing in common.
It looks like a wild jump, but if you look at the underlying physics, the synergy makes perfect sense.
How so?
Well, for the past decade, Aeva has been pouring money and engineering into developing proprietary high-power optical sources and silicon photonics for automotive LiDAR. To make a self-driving car safe, you need a laser that is incredibly reliable, uses very little power, and has exceptionally low noise.
Because it's trying to see things far away.
Right. It needs to bounce a beam of light off a tire on the highway a football field away and measure the return perfectly.
So they basically spent 10 years mastering the exact same high-purity laser tech we were just talking about with Sivers.
That's the core of the strategy. Aeva realized that their proprietary ability to generate and manage high-quality light on a silicon chip is exactly the medicine that next-generation AI data centers are desperate for.
Because of the copper wire bottleneck. Let's dig into that specifically. Why is copper suddenly failing us now after powering the internet for decades?
It just comes down to density and speed. Modern AI chips, like the massive GPUs used to train large language models, are processing data at a mind-bending rate. Moving that much data over copper wire requires pushing a ton of electrical current. That current generates massive amounts of heat, which requires massive amounts of power to cool down.
It's a vicious cycle.
Exactly. Eventually, you hit a physical limit where you simply cannot push any more electrons through the copper without it melting or, consuming more electricity than a small city.
So Aeva is stepping in with their optical tech, and they are targeting two specific acronyms, NPO and CPO.
Near packaged optics and co-packaged optics.
Okay, what's the difference?
Because currently you have an AI chip, and the optical transceivers are placed somewhat far away on the board, connected by copper. NPO brings those optical transceivers very close to the processing chip, minimizing the copper distance.
Okay.
But CPO co-packaged optics is the holy grail of the industry.
By co-packaged, meaning they share the same physical real estate.
Yes. You integrate the lasers and the optical routing directly into the same physical package as the AI processor itself.
Wow, so it's immediate.
The data comes out of the processor and instantly becomes light. You completely eliminate the copper bottleneck. But to achieve CPO, you need optical sources that are high power, incredibly reliable, and deeply miniaturized.
Which again is exactly what Aeva has spent a decade building for cars.
Exactly.
It's a brilliant lateral move, and they are backing it up with serious personnel too. They've appointed Pradeep Srinivasan as the senior VP to lead this new optical connectivity group.
That's a key hire.
Yeah, he was previously their VP of photonics, so he comes equipped with the practical knowledge of how to industrialize and actually mass produce their core photonics tech.
And that manufacturing experience is where companies live or die. Moving a brilliant idea from a prototype to producing millions of units for a data center, that's the hardest phase of hardware development.
And the market seems to believe they can do it. They didn't just announce a goal, they announced they've already signed a joint development agreement with a leading provider of high-speed optical engines to build a module for a major hyperscaler.
And in the tech industry, major hyperscaler is basically code for one of the undisputed giants of the cloud, like Amazon Web Services, Microsoft Azure, Google Cloud.
Big guys.
Right, companies of that magnitude. Securing a development deal with a hyperscaler right out of the gate is a profound validation of Aeva's underlying technology.
And they aren't messing around with the timeline either. They are targeting initial deployment in the second half of 2027, with a full production ramp in 2028.
That is practically tomorrow in hardware development cycles.
It is. Which brings us to the money.
Right.
Because it is one thing to issue a press release about a bold new tech division and an aggressive timeline. Actually executing a hardware pivot of this magnitude requires serious financial ammunition.
Designing, testing, and manufacturing silicon photonics at scale is incredibly capital-intensive.
So here's where it gets really interesting, because I looked at their balance sheet for exactly that reason. Looking at their Q2 2026 earnings, they posted a modest revenue of $6.1 million for the quarter. But their GAAP operating loss for that same quarter was a staggering $34.6 million.
Yeah, they're burning a significant amount of cash on research, development, and scaling.
Right. So I read that and immediately had to push back on their narrative. I mean, if a company is burning over $30 million a quarter, how on earth do they survive the next 2 years to even reach this promised 2028 production ramp?
It looks scary on paper.
It feels like they would run out of gas halfway down the runway.
That is the classic valley of death for hardware startups. But if you look deeper into their financials, they anticipated this exact burn rate.
Oh, really?
Yeah, Aeva recently strengthened its balance sheet with a $115 million follow-on offering. Because they successfully raised that capital, their total available liquidity as of mid-2026 sits at a very healthy $302.9 million.
Okay, so they have roughly $178 million in cash and marketable securities on hand, plus another $125 million sitting in an available facility they can tap into.
Exactly. That $300 million is their war chest. It gives them the necessary runway to absorb those $30 million quarterly losses while they endure the painful process of designing, rigorously testing, and finally scaling these optical connectivity modules for that hyperscaler.
So they have the financial cushion to survive the pivot.
They do.
And the broader market is clearly validating this strategy. Looking at a market chameleon report from early August, the stock was trading around $28 a share.
People are paying attention.
Yeah, the market isn't looking at them as just a car sensor company anymore. Investors see the massive potential of applying a decade of automotive photonics research directly to the exploding AI data center market.
It fundamentally rewrites the narrative of the company.
Although anytime a company makes a huge pivot, I always look at the executive suite.
Naturally.
And the earnings report noted that their CFO of 6 years, Saurabh Sinha, is leaving the company in September 2026 to pursue an opportunity in a different industry. Their VP Corporate Controller, Rupesh Maheshwari, is stepping in as interim CFO.
Right.
The CFO leaving during a massive strategic pivot is usually a huge red flag, isn't it?
It's definitely something analysts watch closely. However, context is everything here. Sinha didn't leave before the capital raise.
Oh, that's true.
He stayed through the successful $115 million funding round and saw the launch of the new optical connectivity division. That timing suggests a planned, structured transition rather than an abrupt, panicked exit.
Okay, that makes sense.
They secured the funding, they set the new direction, and now they're transitioning the financial leadership for the execution phase.
Now, with all this focus and hype around AI data centers, it would be really easy to assume Aeva is just abandoning its roots in automotive sensing to chase the AI gold rush.
Great.
But looking at the rest of their operations, their foundational sensing tech is still aggressively expanding, and frankly, it's what gives their data center ambitions so much credibility.
Exactly. If we connect this to the bigger picture, that major hyperscaler deal we discussed actually relies heavily on the fact that Aeva's technology isn't just theoretical.
Right, it's out in the wild.
It is already proven to work in incredibly harsh, demanding, unpredictable environments.
Let's talk about what that looks like in the real world. In their latest update, they highlighted that Bendix selected Aeva's 4D LiDAR and perception software for the next generation of their advanced driver assistance systems. And this isn't for a quiet luxury sedan driving around a sunny suburb. This system is available on major Class 8 truck platforms in North America. We are talking about massive, vibrating semi-trucks hauling freight across the country.
Which requires an unbelievable level of hardware resilience. Think about the physical environment of a Class 8 truck.
It's brutal.
The sensor is bolted to a chassis that is constantly rattling. It's dealing with freezing temperatures in the mountains, boiling heat in the desert, rain, snow, and constant dust.
And Aeva's LiDAR is 4D. For anyone who only knows 3D LiDAR, which maps the shape and distance of objects, what does the fourth dimension actually add in that chaotic environment?
The fourth dimension is instantaneous velocity. Traditional 3D LiDAR sends out pulses of light and measures how long they take to bounce back, creating a static 3D map.
Like a sonar ping.
Exactly. It takes multiple frames to figure out if an object is moving. But Aeva uses a different technique called FMCW, which utilizes a continuous beam of light.
Okay.
Because of the Doppler effect, the same physics that makes a siren change pitch as an ambulance drives past you, Aeva's sensor can instantly tell not just where every single pixel is, but exactly how fast it is moving toward or away from the truck.
So if a car swerves into the truck's lane, the system doesn't have to guess its speed over multiple frames. It knows its exact velocity instantly.
Yes. And bringing it back to the hardware, to do that requires maintaining perfect optical alignment of a microscopic laser inside a box that is rattling down a highway for hundreds of thousands of miles.
So if their silicon photonics platform can survive life on a freight truck,
then sitting peacefully in a temperature-controlled server rack in a data center is going to be an absolute walk in the park.
that makes total sense. The ruggedness is the actual selling point. And it's not just automotive. They also noted that SNK, a massive industrial sensor company, just launched its first industrial sensor powered by Aeva's precision technology.
Right.
SNK was so impressed they even named Aeva their 2026 Supplier of the Year for innovation and collaboration.
So you have Class 8 trucks with Bendix, factory automation with SEK, and ongoing development programs with giants like Daimler Truck and NVIDIA.
It is a brilliant dual-track strategy. They are monetizing their core technology in the automotive and industrial sectors today, while using that exact same ruggedized, field-tested optical platform to capture the massive upside of AI data centers tomorrow.
It gives that major hyperscaler immense confidence. They know they aren't buying a fragile, unproven lab experiment. They are buying automotive-grade silicon photonics.
So let's take a step back and look at the whole picture of what we've covered today. We started by diving into the manufacturing realities with Sivers Photonics. They showed us the staggering, microscopic physics required to manufacture this future-bonding indium phosphide lasers onto silicon chips with less than 0.3 micrometers of accuracy just to create a pure, reliable engine of light.
They are providing the physical foundation, the capability to bend light to our will at an industrial scale.
And then we saw how Aeva Technologies is taking that exact family of silicon photonics technology and making an incredibly bold leap. They are taking tech designed to give sight to autonomous semi-trucks and dropping it straight into the beating heart of next-generation AI data centers to finally cure the copper wire bottleneck.
It is a brilliant testament to how fundamental breakthroughs in physics, like the hybrid integration of photonics, almost never stay confined to just one single industry.
That's so true.
Once you solve a deep underlying physical problem, the applications just spread like wildfire.
Absolutely. So the next time you use an AI app on your phone or you see a heavily automated truck cruising down the highway, just remember the invisible reality behind it all. You are likely witnessing the real-time application of microscopic hybrid integrated photonic chips working tirelessly in the background, moving mountains of data, not with electricity, but with light.
And I think that leaves us with a truly fascinating question to ponder.
Lay it on me.
If this high-power optical connectivity successfully replaces copper in massive industrial AI data centers by 2028 to solve their heat and bandwidth limits, how long will it be before this microscopic laser technology trickles all the way down to replace the standard electronics inside your own personal smartphone or laptop?
A completely optical computer sitting right in your pocket. Man, that is a wild thought to leave on. Thank you so much for joining us on this deep dive into the optical gold rush. We'll see you next time.